Hello and welcome to our final online lesson. This week I'm going to revise the first 7 weeks of term. Those are the lessons that you studied in the classroom, either with myself or with one of the other teachers. I will not be revising the last 5 weeks of this term because you can watch the videos whenever you wish. So I'm going to be going through a quick introduction, first order equations, second order linear equations, higher order linear equations, and the first half of the chapter about the Laplace transform. From the first chapter, there were 2 key ideas that I talked about: classification of differential equations and direction fields. Classification means, is an equation linear or non-linear? Is it a first order equation, a second order equation, etc.? Is the equation homogeneous or non-homogeneous? I'm going to skip this today. I'm assuming that you are familiar with linear non-linear from linear algebra, and I'm assuming that you understand first order, second order, and homogeneity. I do want to talk about direction fields. In particular, how can we draw a direction field for a first order equation? The idea is we need to draw lots of little arrows in the XY plane. All of these arrows should point to the right. So we might have an arrow like this, we might have an arrow like this, we might have an arrow like this. These are all okay. We should not have arrows pointing to the left. These arrows in red we should not see. All of our arrows should point to the right because we're asking what happens when x increases. And I'm going to do this example. Draw a direction field for the differential equation dy dx is equal to x plus y. I'm going to draw this between minus 2.5 and 2.5 on each axis. On each one of these dots, we need to draw a little arrow to show the slope of the solution. On the left side, I'm going to calculate a few points. For each particular spot, xy, I'll calculate dy dx, and then I'll draw an arrow with the slope of dy dx. For example, let's start at the origin. Let's start at the point 0, 0. We can calculate dy dx is equal to 0 plus 0, or 0. To show that the derivative is equal to 0, we draw a horizontal arrow. Next, the point 1, 0. We can calculate dy dx is 1 plus 0, or 1. To show that the slope is equal to 1, we draw an arrow sloping upwards with slope 1. And so on. At the point 2, 0, slope is 2, arrow points upwards like this. At the point minus 1, 0, the slope is minus 1, so the arrow points downwards with slope minus 1, and so on. At 0, 1, at 0, minus 1, at 1, 1, the slope is equal to 2. At 1, minus 1, the slope is equal to 0, because it's 1 plus minus 1 is equal to 0. Just here at minus 1, 1, again the slope is equal to 0. And minus 1, minus 1, the slope is equal to minus 2. I've calculated the slopes at 10 points. Let me clean this up a little bit. I've drawn these 10 little arrows. I've calculated the slope at 10 points, and I've drawn these 10 little arrows. After this point, we're going to look for patterns, and we're going to make some guesses. The first pattern I'm interested in is the arrows on this diagonal line. This diagonal line contains 3 arrows that we've drawn, and the slope of each of these 3 arrows is 0. It's reasonable to guess that all of the arrows in this region must be the same. It's reasonable to guess that all of these arrows should have slope 0. Next, let's look at a horizontal line, any horizontal line, but let's look at this horizontal line. What happens as we move from the left to the right? As we move from the left to the right, it looks like these arrows are rotating anti-clockwise. It's reasonable to guess that this happens all the way along the line. It's reasonable to guess that if we filled in all of the arrows along this line, they would look like this. Right on the left side, it points downwards, and then the arrows rotate anti-clockwise until they point upwards. We could also look at a vertical line, any vertical line. Let's say the vertical line on x is equal. What happens when y increases? What happens if we start at the bottom and we move upwards? Again, it looks like the arrows are rotating anti-clockwise. Reasonable to guess that all of the way in this region, as we move from the bottom to the top, the arrows will rotate anti-clockwise. Reasonable to guess that the arrows look like this. After we understand these patterns, we can fill in all of the arrows. On each one of these dots, we can draw an arrow now that we understand the patterns. The direction field for dy dx is equal to x plus y looks like this. If I asked you to draw a direction field, you would need to draw lots of little arrows. You would need to draw an arrow on each dot on the grid. For this example, I've drawn 121 little arrows. Moving on, chapter 2 was about first order ordinary differential equations. There were 4 types of equations and then 1 trick, which we used on 2 types of equations in this section. For linear equations, for separable equations, for autonomous equations, for exact equations, and for substitutions, we had different techniques. First, let's talk about linear equations. Consider the linear equation dy dt plus some function p of ty is equal to some function g of t. To solve this differential equation, we need an integrating factor. The equation to remember is that the integrating factor should be the exponential of the integral of the function p. Or to write this another way, e to the power integral of pt. Now what we do is we take our differential equation and we multiply it by the integrating factor. We're going to multiply our equation by mu t to get mu t dy dt plus mu t pty is equal to mu t gt. The next step is to use the product rule on the left side. Because we've chosen our integrating factor carefully, this left side is the derivative of mu y. Using the product rule, our differential equation becomes d dt of mu y is equal to mu g. And then we just need to integrate. The integral of a derivative, these will just disappear, and we'll just be left with mu y on the left side is equal to the integral of mu g. Finally, divide by mu, and we would find our function y. For example, solve the initial value problem ty prime plus 2y plus 4t squared with the initial condition y of 1 is equal to 2. First, we need to write our equation in the standard form. If I go back to the previous slide, we need dy dt plus some function y is equal to some function. Take our differential equation, divide t, we get an equation of the standard form. Dy dt plus some function y is equal to some function. Here, pt is now 2 divided by t. So our integrating factor is the exponential of the integral of 2 over t dt. And when we calculate this, we get t squared. I want to take the equation in the standard form, and I want to multiply it by t squared. We get t squared dy dt plus 2ty is equal to 4t cubed. And using the product rule, the left-hand side is just the derivative of t squared y. When we integrate, the integral of the derivative of t squared y is just t squared y, and the integral of 4t cubed is t to the power of 4 plus c. Dividing by t squared, we get the general solution to the differential equation, t squared plus c over t squared. We also need to use the initial condition. We check that in order to get y1 equal to 2, we need c equal to 1. So the solution to the initial value problem is t squared plus 1 over t squared. Separable equations. In this section, the idea is that sometimes, not always, but sometimes, we can rearrange a first order equation such that the y terms are on the left and all of the x terms are on the right. If, and we emphasize the if here, we can separate the variables like this, then we're allowed to integrate our equation. For example, solve dy dx is y cos x divided by 1 plus 2y. Let's take our equation. I want to rearrange this so that all of the y terms are on the left and all of the x terms are on the right. Y divided by 1 plus 2y squared, I want to move over to the left. It becomes 1 plus 2y squared divided by y. And dx, I want to move over to the right. On the right side becomes cos x dx. Because we've separated the variables, because all of the y terms are on the left and all the x terms are on the right, we're allowed to integrate this equation. The integral of 1 plus 2y squared over y dy is equal to the integral of cos x dx. And you can check that when we calculate these integrals, we get ln of the absolute value of y plus y squared is equal to sine x plus some constant c. For the equation, we can leave the solution in this form. Moving on quickly, equations of the form dy dt is equal to f of y are called autonomous equations. The key point here is that the function f only depends on y. There are no t variables in the equation. It's just dy dt is equal to some function of y. Autonomous equations have equilibrium solutions, also called critical points, where we have dy dt is equal to 0. The way that we can study autonomous equations is we can draw the graph of f of y against y, and where f of y is positive, we can draw a green arrow pointing to the right. Where f of y is negative, we draw a green arrow pointing to the left. We do this so that we can understand the stability of equilibrium solutions. If all of the green arrows around the point are pointing towards the point, then the equilibrium solution is asymptotically stable. If we have an interior point, we would expect to have an arrow on the left and an arrow on the right. If they're both pointing towards it, then we know that the equilibrium solution is asymptotically stable. If we have an end point, then we're only going to have one arrow beside the point, either pointing towards it or pointing away from it. If the one and only arrow is towards it, then again, the equilibrium solution is asymptotically stable. If the opposite happens, if all of the green arrows are pointing away, then we know that the equilibrium solution is unstable. And finally, if we have an interior point where the arrow on one side is pointing away, but the arrow on the other side is pointing towards, then we have that the equilibrium solution is semi-stable. For example, find all of the equilibrium solutions of dy dt is equal to some function of y, f of y, which in this case is 7 minus y, 2 minus y, 7 minus y, 4 minus y, and classify each equilibrium solution as asymptotically stable, unstable, or semi-stable. This should look familiar to you because this is a question from the first midterm exam. The way that I've written this function, it's easy to see that equilibrium solutions are y is equal to 2, y is equal to 4, or y is equal to 7. But are these asymptotically stable, unstable, or semi-stable? This is a graph of f of y against y, which I showed you in the midterm exam. I want to draw green arrows in each interval, which is between the equilibrium solutions and to the left and the right of the equilibrium solution. First, between 0 and 2, the function is positive, so our green arrow should point to the right. Between 2 and 4, the function is negative, the green arrow should point to the left. Between 4 and 7, the function is positive, the green arrow should point to the right. And if y is greater than 7, again, the function is positive, the green arrow should point to the right. Now we can see if each one of these points is, each one of these equilibrium solutions or critical points is stable, unstable, or semi-stable. First, look at 2. All of the arrows are pointing towards 2. This one is stable. At 4, all of the green arrows are pointing away from 4. This point is unstable. At 7, the arrow on the left is pointing towards 7. The arrow on the right is pointing away from 7. So this point is semi-stable. The next type of equation, next type of special first order equations, were exact equations. Consider some function m plus some function n, y prime is equal to 0. We had a theorem that said this equation is exact if and only if the partial derivative of m with respect to y is equal to the partial derivative of n with respect to x. And if we know that the equation is exact, then we can find some function psi of x and y such that x derivative of psi is equal to m and the y derivative of psi is equal to n. After we find this function psi, we have the solution to the differential equation is psi is equal to some constant. For example, consider y cos x plus 2x e to the power y plus sine x plus x squared e to the power y minus 1, y prime is equal to 0. Is this differential equation exact? If the answer is yes, solve it. For this equation, m is y cos x plus 2x e to the y, and n is sine x plus x squared e to the power y minus 1. The derivative of m with respect to y is cos x plus 2x e to the y. The derivative of n with respect to x is also cos x plus 2x e to the power y. Because these are the same, we know that the equation is exact. Because it's exact, we know that there exists the function psi. In particular, there exists psi such that psi x is m, y cos x plus 2x e to the y, and psi y is n, sine x plus x squared e to the power y minus 1. We pick one of these equations, it doesn't matter which one, we pick one and we integrate it. I'm going to pick the first equation and I'm going to integrate it with respect to x, because psi is the integral of the derivative of psi, which for us is y sine x plus squared e to the power y plus, and this is important, because we're integrating with respect to x, what would normally be the constant of integration is in fact a function of integration. Because we're integrating with respect to x, the function must be a function of the other variable or variables, which in this case is y. First, I integrated with respect to y, then I differentiate. So first I integrate with respect to x, and then I want to differentiate with respect to the other variable. Differentiating with respect to y to get sine x plus x squared e to the power y plus h prime of y. But we already have a formula for psi y. We already know that psi y is sine x plus x squared e to the power y minus 1. So we know h prime. We know that h prime must be minus 1. We can choose any function h which satisfies this. So let's choose h of y is equal to minus 1. Why can we choose any function? Because later on we're going to be adding a constant. We don't need two constants. We'll add the constant later instead of adding it now. As soon as we know h, we know psi. Psi is sine x plus x squared e to the power minus y. And as soon as we know psi, we know the solution to the differential equation. Psi is equal to a constant. There was a more advanced technique in this section. Sometimes we can change an equation which is not exact into an exact equation by multiplying by a special function called an integrating factor. Sometimes our integrating factor will be a function of x. Sometimes our integrating factor will be a function of y. And not in this course, but more generally, sometimes it's not possible to find an integrating factor. There are two equations which we need here. If you do in a classroom exam, you would be expected to memorize these two equations. Because we're doing an online exam, obviously you will write these down on a piece of paper before you start. If we're looking for a function only of x, we're going to be considering the equation d mu dx of x is my minus nx over n multiplied by mu x. If we're looking for a function mu or only of y, the equation that we're going to use would be d mu dy of y is nx minus my over m mu. For example, solve the equation y e to the power xy plus 2 over y plus x e to the power xy multiplied by y prime is equal to 0. For this equation, my is e to the xy plus xy e to the xy, and nx is e to the xy plus 2 plus xy e to the power xy, which is not the same as my. This equation is not exact. Can we change it into an exact equation using an integrating factor? To try to understand, I'm going to calculate my minus nx over n and nx minus ny over m. The first one, when we calculate this, we get minus 2 over y plus x. In this function, we have x and we have y. We don't want this. We only want to have x. So we can't use this. This is no good. When we calculate nx minus my over m, we get 2 divided by y. There's only y here. There's no x here. This is only a function of y. This is what we want. We're going to use this one. Since the second one is a function only of y, we're going to look for an integrating factor mu, which is a function of y. There's a mistake here. There should be an extra mu just here. It should say d mu dy is equal to 2 over y mu. The solution to d mu dy is equal to 2 over y mu, and I'll ask you to check this, is equal to y squared. So this is our integrating vector. We're going to multiply our differential equation by y squared. After we've multiplied by y squared, we get y cubed e to the power xy plus 2y plus xy squared e to the power xy y prime is equal to 0. If we've chosen our integrating factor correctly, this equation should now be exact. To make sure we didn't make a mistake, it's worthwhile checking this. We can calculate my is 3y squared e to the xy plus xy cubed e to the xy, and we can calculate nx is the same function. Because they're the same, we now have an exact equation. You know how to solve exact equations, so I'm just going to tell you that the solution is y squared e to the power xy is equal to some constant c. And I leave this for you to check. Please finish this example, check that this really is the solution. The final idea from chapter 2 was the idea of substitutions. Some of the other teachers may have mixed this into other sections. If you have the textbook by Boyce and DePrima, it's hidden in the exercises. They don't have a section just for this, they just have exercises. But I think it's worthwhile making this its own section. We can use substitutions to solve two different types of equations: homogeneous equations and Bernoulli equations. First, homogeneous equations. The differential equation dy dx equal to f of x and y is homogeneous if we can write it in as the form dy dx is equal to some function of y divided by x. The key step for a homogeneous equation is we're going to use a substitution. We're going to use a substitution. V is equal to y divided by x, or to say this another way, y is equal to x multiplied by v of x. Now note that if we use the equation in the red box, and if we differentiate this using the product rule, dy dx is equal to v plus x dv dx. For example, solve dy dx equals to y minus x divided by x minus y. This equation is a homogeneous equation because if we divide the top and the bottom by x, we get y divided by x minus 4 and 1 minus y over x. Each term in here is a y divided by x. In other words, this is a function of y divided by x. So we can do our substitution. We can replace y divided by x by v. Instead of y of x minus 4, we get v minus 4. Instead of 1 minus y of x, we get 1 minus y. And using the calculation on the previous page, instead of dy dx, we write v plus x dv dx. Rearrange this to solve for x dv dx. We get x dv dx is equal to v squared minus 4 divided by 1 minus v, which you can check. This is a separable equation. You know how to solve separable equations. Let me go through very, very quickly. We can rearrange this equation so that all of the v terms are on the left and all of the x terms are on the right. If we can do this, then we're allowed to integrate. Using partial fractions and then integrating and then changing back to y. I'm skipping a lot of the steps here. I'm leaving this for you to finish. We obtain the solution y plus 2x cubed, y minus 2x is equal to c. Good exercise for you would be to complete this example, fill in all of the details. The idea for homogeneous equations is we use the substitution of v equal to y divided by x to change our equation into a separable equation, and then we only need to solve a separable equation. This was actually a midterm exam question. How do we solve homogeneous equations? We use the substitution v is equal to y divided by x. The second type of equation that we can use substitutions for is Bernoulli equations. If we have an equation of the form y prime plus pt of y, so pty is equal to qty to the power m, this is a Bernoulli equation. To solve a Bernoulli equation, we use the substitution v is equal to y to the power 1 minus n. Now the key is if we have y to the power n on the right-hand side, we use the substitution v is equal to y to the power 1 minus n. For example, solve dy dx minus 3 over 2xy is equal to y to the power minus 1. Just here I have y to the power n, y to the power minus 1. For this equation, n is equal to minus 1, so we're going to use the substitution v is equal to y to the power 1 minus n, which for us is y squared. We can rearrange this and we can write this as y is equal to the square root of v. Anytime we have a Bernoulli equation, we start with the substitution v is equal to y to the power 1 minus n. Then what we do is we use the chain rule. Dy dx is dy dv, dv dx, which for us is a half, v to the power minus a half, dv dx. And then we substitute this into the differential equation. Instead of dy dx, we have a half v to the power minus a half dv dx. Instead of y, we have v to the power of a half. And instead of y to the power minus 1, we have v to the power minus a half. To simplify this, we can multiply by 2v to the power half, and our equation simplifies to dx minus 3 over xv is equal to 4x. This is a linear equation. You know how to solve linear equations. You can check that the solution to this problem is minus 4x squared plus cx cubed. After we know v, we know y. Simply replace v by y squared to obtain the solution. Y squared is minus 4x squared plus cx cubed. Let me just quickly recap the idea. For a Bernoulli equation, the idea is we use the substitution v is equal to y to the power 1 minus n, and then we solve a linear equation. Chapter 3 was about second order linear differential equations. I'm going to talk about homogeneous equations with constant coefficients. I want to talk about reduction of order. And then I want to talk about two methods to find a particular solution to a non-homogeneous equation. Consider the equation ay double prime plus by prime plus cy is equal to 0 for some constants a, b, and c. We can write down the characteristic equation, ar squared plus br plus c is equal to 0. We want to find the roots of the characteristic equation. There are three possibilities. Either the roots are real and different, they might be complex numbers, in fact complex conjugates, or the root might be a real number, but it might be repeated. To write down the general solution to ay double prime plus by prime plus cy is equal to 0, we need to find two linearly independent solutions, y1 and y2. And then the general solution is a linear combination of these two solutions, c1 y1 plus c2 y2. We studied the three different cases and we saw which solutions we should use. The first case, the easiest case, if we have different real roots, then our two functions are e to the r1t and e to the r2t. If we have complex conjugate roots, lambda plus I mu for real numbers lambda and mu, then our two functions are e to the lambda t cos mu t and e to the lambda t sin mu t. If we have repeated roots, two real roots but they are the same number, then our two functions are e to the r1t and t multiplied by e to the r1t. If I give you a problem like this, you will need to remember the information on this slide. Reduction of order was something we spent time on. Consider y double prime plus pt y prime plus qt y is equal to 0. And suppose that we know one solution to this equation, and we want to find a second linearly independent solution. What do? We make a guess. We guess that the second solution, y2, is some function v multiplied by y1. Using this guess, we find that after we've done some calculations, instead of needing to solve a second order differential equation, we only need to solve a first order differential equation. We reduce the order of the equation that we need to solve. One example. Suppose that we're told that y1 equal to t solves the differential equation t squared y double prime plus 2ty prime minus 2y is equal to 0. And we're asked to find a second linearly independent solution. Start with the key idea. For reduction of order, we always want to start with y2 is equal to vt multiplied by y1. We say this again. If I give you a reduction of order question in the final exam, you will want to start with y2 is equal to v multiplied by y1. For this example, y1 is equal to t, so we're going to start v of t multiplied by t. Then we calculate y2 prime, y2 double prime, and we substitute these into the differential equation and simplify to get t squared multiplied by tv double prime plus 4v prime. Now, the key point is the unknown v terms. We have v double prime and we have v prime, but we have 0 v. When we do reduction of order, we must always have no v terms or 0 v terms. If you don't get 0, if you get any v terms at all, then you've made a mistake. You need to go back and find your mistake. We can have v double prime terms, we can have v prime terms, but we must not have terms involving v. And the reason is that we want to make a substitution. Instead of writing v prime, I want to write u. Let's look at the differential equation from the previous page. 0 is equal to t squared tv double prime plus 4v prime. This must be true for all t, so we can forget about the t squared. We must have that tv double prime plus 4v prime is equal to 0. Instead of v prime, we're going to write u. Instead of v double prime, we have the derivative of u. We have a first order differential equation. We need to solve this to find u. This equation is a separable equation, and it's also a linear equation. I'm choosing to solve this as a separable equation. We can calculate that u must be some constant, small c, multiplied by t to the power minus 4. After I know u, I can integrate to find v. We can find that v must be the integral of u, which is minus 1/3 ct cubed, so t to the power minus 3 plus k. At this point, we can choose c and we can choose k. Let me repeat, y1 was equal to t, y2 is vt multiplied by t, or minus 1/3 ct to the power minus 2 plus kt. We can choose c and we can choose k. We're trying to find a solution which is linearly independent from y1. So we don't need this plus kt on. This doesn't make us linearly independent, this is just some extra bit. So I want to remove this. To remove the kt, I'm just going to choose k equal to 0. And then I want to make this function a little bit easier, just because I like easy numbers. Instead of this minus 1/3 c, I want this to just be 1. So I'm just going to choose c as minus 3. This makes our solution easier. It makes y2 equal to t to the power minus squared. And this could be the answer to the problem, as long as we're sure that this is correct. But does it really solve the equation? Does t to the power minus 2 really solve t squared double prime plus 2ty prime minus 2y is equal to 0? If you have time to exam on scrap paper or as part of your answer, it's worth just checking that your answer is correct. We can calculate the first and second derivatives of this function, put them into the differential equation, and we can find that we get equal to 0. So the answer is yes. This function really does solve the differential equation. It's very quick to do this check, very quick to check if your answer is correct or not. Another thing I might ask is, are these two functions linearly independent? If I ask you if two functions are linearly independent, we need to use the Wronskian. The Wronskian is y1, y2, y1 prime, y2 prime. When we calculate it for these two functions, we get minus 3t to the power minus 2, and as long as t is, and because we're told that t is not 0, this is not equal to 0. If the Wronskian is not equal to 0, then our two functions are linearly independent. Non-homogeneous differential equations. Now let's suppose we want to solve a y double prime plus by prime plus cy is equal to some function g of t. There's 3 steps we need to do. We need to find the general solution to the homogeneous equation. We need to find one solution to the non-homogeneous equation. This one solution is called a particular solution. And then we add these two together. The solution we find in step 1 plus the solution we find in step 2. How do we do step 2? We've studied 2 methods to do step 2. The first method was the method of undetermined coefficients. The idea in this method is We look at the function gt and we make a guess, which includes constants. And then we need to try to find the constants. If we can find the constants, then we have our particular solution. For example, solve y double prime, 2y prime plus y is equal to 2e to the power minus t. There's a mistake here. This should be equal to 0. The homogeneous equation y double prime plus 2y prime plus y is equal to 0 has characteristic equation 0 is equal to r plus 1 squared. We have repeated root minus 1, so the general solution of the homogeneous equation is c1 e to the power minus t plus c2 t e to the minus t. Next, we need to find a particular solution to our differential equation. We look at our function gt, we look at 2e to the minus t. Now, we can't guess a constant multiplied by e to the minus t because we have e to the minus t in our general solution of the homogeneous equation. So next we think, what if we multiply by t and we guess t e to the minus t? No, we can't use that because we have t e to the minus t in our general solution. For this equation, we need to guess t squared e to the power minus 2, and then multiply by some constant a. Let me repeat this idea. If instead of 2e to the t we had some different function, let's just say we had the function cos t, we might guess that our solution had cos and sine. That would be okay because cos and sine do not appear in the general solution of the homogeneous equation. But for this equation, because we have e to the minus t in the general solution, we can't guess e to the minus t. Because we have t e to the minus t in the general solution of the homogeneous equation, we cannot guess t e to the minus t. So we multiply by t again, and we're going to consider the guess, or the ansatz, a t squared e to the power minus t for some constant capital A. We can differentiate capital Y a couple of times, put them in the equation, and find that we must have 2 to the power minus t is equal to 2a e to the power minus t. So clearly capital A must be equal to 1. We have found our particular solution. T squared e to the power minus t is a particular solution to this differential equation. Let me repeat, we have the general solution to the homogeneous equation and a particular solution to a non-homogeneous equation. To finish this problem, we add these together. The general solution to the differential equation in the question is the general solution to the homogeneous equation, and then plus a particular solution. We also talked about the variation of parameters method. This is another way to find a particular solution. And this relies on a theorem. The equation to remember, or to write down before the exam, is that a particular solution is given by minus y1 integral of y2 g over w, that's y2, integral of y1 g over w, where y1 and y2 form a fundamental set of solutions of the homogeneous equation, and W is the Wronskian of y1 and y2. For example, solve y double prime minus 2y prime plus y is e to the power t ln t. Note we have a complicated function here. If we have an easy function g, probably we want to use the method of undetermined coefficients. If we have a complicated function, then probably we want to use variation of parameters. First of all, we write down the characteristic equation, we find roots, and then we find a fundamental set of solutions of the homogeneous equation, and we calculate the Wronskian of these two functions. For us, w1 is e to the power t, sorry, y1 is e to the power t, y2 is t e to the power t, and w is e to the power 2t. I think there's a mistake here. This function should be over here. And then we use our formula to calculate the particular solution. We start with our formula, minus y1 integral of y to g over w plus y2 integral of y1 g over w. And after we put our functions in, and then cancel, we find we have minus e to the power t, integral of t ln t dt, plus t e to the power t integral of ln t dt. For the first integral, we need to use integration by parts. For the second integral, I rely you remembering from calculus 2, mathematics 2, that the integral of ln t is t ln t minus t. And when we simplify this, we get a half ln t minus 3/4 t squared e to the power t. Therefore, we have the general solution to a non-homogeneous equation. First, the general solution to the homogeneous equation, and then plus the particular solution which we've just found. Next, I talked briefly in class about chapter 4, higher order linear differential equations. The ideas from chapter 4 were the same as the ideas from chapter 3. The only difference is we need to have more functions in the fundamental set of solutions. If we're studying a third order equation, we need 3 solutions in the fundamental set of solutions, and so on. If we're studying, let's say, a 7th order equation, then we need 7 functions in our fundamental set of solutions. Other than that, the idea is the same. We write down the characteristic equation, we find the roots, and then we use the same ideas from before. In the final few slides, I want to talk about the Laplace transform. We talked about more advanced techniques in our first online lesson. I want to recap the start of this chapter. The Laplace transform takes some function small f, and it gives us a new function capital F, using the formula integral from 0 to infinity e to the power minus st f t dt. We did some examples in class. We calculated some Laplace transforms. For example, we calculated that the Laplace transform 1 is 1 over s. We calculated that the Laplace transform of e to the power at is 1 over s minus a, etc. Some of these Laplace transforms I did in class. Some of them I've asked you to do on the homework sheets. I assume that for the exams you have some table like this by your side. Why do we use the Laplace transform? Because the Laplace transform eats derivatives. The important formula to use is that the Laplace transform of f prime is equal to s multiplied by the Laplace transform of f minus f of 0. If we use this equation 2 times, we can find the Laplace transform of f double prime. If we use the first equation 3 times, we could find the Laplace transform of f triple prime and so on. We just note the pattern here. 3 derivatives, we start with s to the power 3, and then it goes s to the power 2, s, and then s to the power 0. And we could just repeat this if we wanted to. We could calculate the Laplace transform of the nth derivative of f. Start with s to the power n, Laplace transform of f, and then it goes s to the power n minus 1, s to the power n minus 2, and so on, down to s, and then s to the power 0. We can use this to solve differential equations. The idea is, let's suppose we're starting with a difficult differential equation, and we want to solve this to find the function small y. But let's suppose we can't do this directly. What we can do is we can use the Laplace transform to change our difficult equation into an easy equation. If it's an easy equation, we can solve it to find a formula for capital Y. If we know capital Y, then perhaps we can take the inverse Laplace transform to find small y. Instead of having to solve a difficult equation, we use the Laplace transform, we solve an easy equation, and then we use the inverse Laplace transform. For example, solve the initial value problem, fourth derivative of y minus y is equal to 0, with the initial conditions y of 0 is 0, y prime of 0 is 1, y double prime of 0 is 0, y triple prime of 0 is equal to 0. Using the Laplace transform, we can take the Laplace transform of the differential equation. The Laplace transform of 0, of course, is just 0, is equal to the Laplace transform of fourth derivative of y minus the Laplace transform of y. Using the formulas on a previous page, the Laplace transform of the fourth derivative of y is s to the power 4 capital Y minus s cubed y 0 minus s squared y prime 0 minus s y double prime 0 minus y triple prime 0. And then we have minus the Laplace transform of small y, or minus capital Y. In the question, we're told that y of 0 is equal to 0. So this term is just equal to 0. We're also told that y prime of 0 is equal to 1. This becomes just minus s squared. We're told that y double prime of 0 is 0. This term is just 0. And we're told that y triple prime is 0 is 0. So this term is just 0. We are left with s to the power 4 capital Y minus s squared minus capital Y, which I could write as s to the power 4 minus 1 capital Y minus s squared. Rearrange this. Capital Y is s squared over s to the power 4 minus 1, or using partial fractions, a half over s squared minus 1 plus a half over s squared plus 1. To finish the problem, we can take the inverse Laplace transform of capital Y. Small y must be a half multiplied by the inverse Laplace transform of 1 over s squared minus 1 plus a half multiplied by the inverse Laplace transform of 1 over s squared 1. These two functions we can find on our table of elementary Laplace transforms. we can find that this is a half sine t plus a half sine t. This was a revision of the first 7 weeks of term. This is a very quick recap of my 7 weeks of lessons, although your teachers may have taught you in a different order. For the last 5 weeks of classes, you can watch the videos on the O-Level Blackboard. And this is the end of your differential equations course. Do you have any questions which you'd like to ask in the chat?